What's up, Vsauce? Alex here with star types and spectral classes. The introduction to this is the Hertzsprung-Russell diagram, which is super important for general astrophysics. So in 1911, the Danish astronomer Enyar Hertzsprung plotted the absolute magnitude of stars against their color. No one had ever done this before, and he wanted to see if there was a correlation between the two characteristics. Now, the absolute magnitude is the brightness of a star if it were exactly 10 parsecs away from Earth. Contrary to what Star Wars would have you believe, a parsec is not a unit of time, it is actually a unit of distance. Absolute magnitude is thus a way to very empirically measure the brightness of a star. Now, the color of a star is really used to indicate its temperature. So a blue-colored star or a whitish star will tend to be much hotter than a red star because there is more energy in blue light than there is in red light. Now, at the same time, an American astronomer, whose name was Henry Norris Russell, did the same thing, but he used the spectral class of a star instead of color to measure temperature. Spectral class effectively is the same thing as a star's temperature. The key difference between the two is that spectral class determines the materials which a star is made of so that you can very objectively determine temperature, rather than just saying, oh, this is blue, or this is bluish white, or this is light blue. And this is what happened when they plotted these results. So as you can see, you have this very clear diagram created. It shows that there is indeed a relation between a star's luminosity, its brightness, and its temperature. Stars that are brighter tend to be hotter at the same time, while stars that are cooler tend to be less bright. This also grouped most stars into 4 distinct categories. There is the main sequence, making up this little bar across the center of the diagram. Then there are the white dwarfs, which are like this bottom left corner. Then you have the giants just above the main sequence, and the supergiants above those. Now we're going to get into the major star groups. The first group that we're going to go over is the main sequence, the little diagonal bar across. Now these are relatively young stars. This is the first stage in what is generally considered stellar evolution. Now, because these stars are so young and our galaxy itself is fairly young as galaxies go, these are the most common star group in the Milky Way. The lifespan of these stars depends very heavily on their mass. Very heavy, very large stars will tend to evolve quickly out of the main sequence, while low-mass stars will evolve much more slowly. Because these stars make up the diagonal bar across the Hertzsprung-Russell diagram, they have varying temperatures and magnitudes. You have some very cool, very dim stars way in one corner, but also some very hot and some very bright stars in the other. Whether a main sequence star is very bright or very dim depends mostly on its class within the main sequence. These are the spectral types, and I will discuss them later. Our sun is currently on the main sequence of stars. It's right in the middle here, so it's not super bright, but it's also not super dim. All stars present on the main sequence will eventually evolve to the other groups. Next up we have the giants. These are just above the main sequence of stars. They are middle-aged with a relatively medium lifespan. Now, giant stars tend to be old enough that they have used up most of the hydrogen fuel that they had when they were on the main sequence. Because they have used up their hydrogen fuel, they kind of undergo a midlife crisis. They switch from fusing hydrogen to fusing helium. And helium fusion releases so much energy that the star actually kinds to blow itself up. It expands to many times its original volume. Giant stars tend to have very high luminosities. They're some of the brightest stars in the sky, but they also have a pretty low temperature. The reason that they have a very low surface temperature is because their surface is enormous. The helium fusion has expanded the star's volume so much that it actually forcibly cools it. Now, giant stars have 2 different fates. Now, if they are particularly large, giants will become supergiants once their helium has been exhausted. If they're smaller like our sun, they will instead become a white dwarf. Next up are the supergiant stars. Supergiants are very old stars with very short lifespans. Supergiants are typically medium or high-mass stars from the main sequence which have completely exhausted their supply of both hydrogen and helium available for fusion. Because these stars have used up all their hydrogen and helium, they've started fusing things like carbon, nitrogen, and oxygen depending on their mass. These stars tend to have very high luminosity and a variable temperature. So they're all super bright, but there are some that are very hot, like Rigel and Deneb, while there are some that are very cold, like Betelgeuse. Like the normal giants, these stars also have 2 different fates. The very largest of supergiants will turn into black holes. while somewhat smaller ones will form neutron stars. Regardless of their particular fate, every sort of supergiant will always generate a supernova when it dies. Next up are the white dwarfs. White dwarfs are often very old stars which have lost most or almost all of their mass. White dwarfs are actually so unmassive that they are unable to continue the nuclear reactions that stopped them from collapsing when they were on the main sequence. White dwarfs are some of the dimmest stars that exist. In fact, some of them are so dim that they're only known because of their gravitational effects and cannot actually be seen. White dwarfs are so dim because they're not performing nuclear fusion anymore. They're not actually producing new light. They're only emitting light as they cool. It's like taking a very hot frying pan and setting it on the side, and it glows, but it's not undergoing nuclear synthesis. White dwarfs are the final state for the small or medium stars on the main sequence that don't have the mass to become black holes or neutron stars. The Sun itself will become a white dwarf in several billion years. Now we'll really quickly go through the spectral classes of the main sequence. Technically, these classes exist for every star regardless of whether or not it is main sequence, but they're only really important for the main sequence stars. The first of the classes we'll go over are the ones that are really, really big. The first of these is called Class O. Now, these are the largest, hottest, and brightest stars on the main sequence. They appear bluish-white and contain ionized helium. They're actually so hot that they can ionize a noble gas. If you're in AP chemistry, you know that this is not hard to do. Class O's are so energetic that they can. These are also the least common of any of the spectral classes. There are the fewest of them up here. Next up are Class B stars. They are slightly smaller, slightly cooler, and slightly dimmer than Class O stars. They appear to be this weird bluish-white color, and they contain neutral helium. They're not quite energetic enough to fully ionize noble gases any longer. After Class B are the Class A stars. I know the alphabet doesn't work. These are smaller, cooler, and dimmer still than Class B stars. They appear to be just a solid white color, and they contain ionized metal. Next up, you have the medium-sized stars of the main sequence. The first of these is the Class F star. Class F stars are even smaller, cooler, and dimmer than Class A stars are. A general trend as you go down the main sequence from the top right corner to the top left corner is that stars get smaller, cooler, and dimmer. Class F stars are a yellowish-white color, and they contain a lot of neutral metals. So in a Class F star, you might find unionized iron, whereas in a Class A star, you would probably find like iron 2+. And then you have Class G stars. These are again smaller, cooler, and dimmer than Class F stars. They're this yellowish color, and they contain a lot of calcium ions. The Sun is one of these stars. It's right down here towards the end of this. Next up, you have the very smallest stars on the main sequence. These include Class K, which is this one right here. These are, again, smaller, cooler, and dimmer than Class G stars. They appear to be this yellowish-orange color, and they contain a lot of titanium oxide. Something that you might want to know about titanium oxide in case you take an advanced chemistry course or go into Science Bowl or Quiz Bowl is that it's involved in a lot of paints because it has very interesting chromatic properties. I don't know if this will be in the guide next year, but it's just something cool to know. The last of the 7 classical types of spectral classes is Class M. These are the smallest, coolest, and dimmest of all the stars that exist. Class M stars appear to be red and contain quite a lot of titanium oxide as well. Class M stars, also known as the red dwarfs, are the most common of all spectral classes. They dominate in the Milky Way and indeed in most galaxies that we know of. These are the sources that I used. Most of them are for the images, but quite a few of them are for the research that I did as well.